Come to my classroom. Today's topic is physics of rainfall. In fact, for studies of soil erosion, estimation, then watershed management, then flood management, then even design of soil and water conservation practices, we require the rainfall data, or you can say we require various rainfall parameters. Because these rainfall parameters, they constitute the erosive value, the energy value of rainfall, which leads to detachment of soil particles and ultimately soil erosion to take place. Because as we discussed in our previous lectures, soil erosion takes place when detachment and transportation of soil particles is there. So, for that, this is very important that we should have a knowledge about various rainfall parameters in a particular region. Similarly, this rain parameters are rain amount, the most important one, then distribution of rain, what is the amount of rain, how it is distributed, and at the same time its energy load. So, energy load, it will depend upon the intensity of the rain. What is the velocity of the rain? Rain intensity as well as rain's drop size. So, we will be studying these parameters one by one in over here. Now, first of all, as I said, rain amount or quantity of rain. So, the first is quantity of rain. This is basically the volume of rain, volume or depth of rain falling at ground surface. So, this can be expressed in, if its volume, that is liters or cubic meters or even millimeter or centimeter. So, when we say millimeter and centimeter, so that means these are the depth units of rainfall. Now, for example, 1 centimeter of rainfall, it is falling on an area of 1 square kilometer. So, 1 centimeter of rainfall falling on an area or spread on an area of 1 square kilometer, this amounts to 10 raised to power 4 cubic meters, or you can say 10 million liters. So, see the importance. Simply 1 centimeter of rainfall falling on an area of 1 square kilometer, this amounts to 10 million liters. 10 million liters, these are basically, this is the volume of rain water. On the other hand, so we can say that this is 1 centimeter of rain. So, this could be on 1 hectare of land, 1 acre of land. So, you can then calculate the total volume because depth multiplied by area, that will give you total volume of rainfall. So, this is the importance of quantity, that is rainfall, and this can be measured by recording and non-recording rain gauges. Recording rain gauge and non-recording rain gauge. Now, non-recording rain gauge is simply, it's a container. If this is container and here its upper part has a funnel, so water is collected over here. So, rain water gets collected in this container and you can measure it with simply this is measuring cylinder, this is marked with depth unit 1, 2, 3, 4, 5. So, this is in centimeters. So, this measuring cylinder comes with the recording rain gauge, but if you do not have the measuring cylinder, then it is no problem. You can use any type of container, you can use a simple bucket and then measure the amount in a volumetric cylinder, collect the rainwater in any cylindrical container or in any container. Why cylindrical? And measure it with a measuring cylinder, simply measuring cylinder. So, supposing this comes out to be 240 cubic centimeters. The volume of water which is collected in this container, that is 240 cubic centimeter. Then you have to record this collecting area. This area, supposing this comes out to be 120 square centimeter. So, 120, this will be 2 square centimeter. So, this comes out to 2 centimeter. So, that means 2 centimeter of rain has been recorded. Then you can calculate the volume of rainwater over different areas, say 1 acre, in 2 acres, 10 acres, 1 hectare, 100 hectare, 1 square kilometer, whatever you want to calculate. So, that is why depth units are more important. We are not concerned mainly if somebody says today 10 million liters of rain occurred, that does not convey any meaning. 10 million is just on a area of 1 square kilometer. So, it does not convey that on what area 10 million liters of rain water fell. On the other hand, if I say 1 centimeter of rain occurred, that is understandable. You can calculate, okay. So, my field area is 1 acre, so I can calculate how many liters. If my field is 1 hectare, I can calculate. So, like that. So, that is why we generally express the quantity of rain on depth units, and that is in millimeters or centimeters. So, after this we have distribution of rain. After quantity of rain, the second important parameter is distribution of rain. Now, rain distribution perhaps is much more important than amount of rain. Why? Because sometimes what happens that you have say over a period of 3 months, you have rainfall of 600 millimeters. But on the other hand, that 600 millimeter of rainfall occurred just on 10 days. Those 10 days could be 2 plus 3 plus 4 plus 5, or those could be 8 plus 2, or those could be 5 plus 5. So, that determines. So, that means for the rest of 80 days there was no rainfall. So, then from agriculture point of view, at least this rainfall does not convey any meaning. So, and because it occurred in a very short period of 10 days, and those 10 days could be consecutive 10 days or it could be spread over. So, the question is this distribution now it has this distribution could be over the time and over the space. It could be temporal as well as spatial. But generally on a broader sense, if we see if the rain distribution, I will better draw over here a diagram. If rain distribution is spread throughout the year, that means every month you have some rain like this. So, from January, February, March, April, May, June, July, September, October, November and December. So, here the rainfall is almost in every month. So, throughout the year you have some rain, little or more, whatever it is. So, we call this as uniform distribution. So, here is the rain amount. So, you can say throughout the year you in every month you have some amount of rainfall, it is uniformly spread. So, this type of, so our second point was rain distribution. So, amount and distribution, distribution is more important than this. So, here the first point is your uniform. So, this is uniform distribution and this is good. Of course, this is good from water sources point of view, but here the issue is that if you are taking one or two crops, you have little window period for harvest of the crop. When the crop is at the ripening stage and you are going to harvest within 10, 15, 20 days, you need to have a dry period. So, I should say that from agriculture point of view, this is not so good distribution. On the other hand, you may have a situation where, sorry, so in this case the rain is, I need to, so here the rain is distributed in say in January, February, March, April. So, this is one period. Then you have here, then you have a dry spell. This is dry period. So, this is one wet period and then you can have another wet period. So, we call this as bimodal distribution. That means during a particular year the rainfall is concentrated in two particular periods. So, we call this as bimodal. This is good from agriculture point of view, because here for both the crop seasons, if you have two crop seasons in a year, you have a window period for harvest and next sowing of the crop. So, we consider this bimodal as agriculturally desirable, and this is generally the characteristic of subtropics. This is yes, subtropics. Subtropical regions. Whereas the uniform distribution, this is the characteristic of mostly the temperate regions. They have low intensity rain spread throughout the year, what we call as uniform distribution, then bimodal. Then third type is when your rainfall is concentrated during one single part of the year. That means here you have rainfall, here this is all dry period. We call this as unimodal. So here the rainfall is concentrated during one part of the year, maybe 3 months, maybe 4 months, and this generally happens in tropical regions. So we call this as unimodal. So this is about the distribution of rainfall. As I said, this is very important. Now, if even during a particular, say this is wet period, in wet period, as I said, if it's spread over 3 months, that means 90 days, but you are getting the rain only for 10 days, and then in between you have dry spells, then this type of rain will not be good from agriculture point of view. So fair distribution even during that particular period, whether it is unimodal, whether it is bimodal, or even if it's uniform, you should have rain should be spread over the 90 days period at least. So that will be good from it can be less erosive also, and it is agriculturally good also, it's beneficial for the crops. So if it's not spread over a particular period, distribution is not good, then from agriculture point of view this will not be a desirable practice. So after rain distribution, the third parameter which we have is rain intensity. This is again an important parameter, that okay, your amount is good, distribution is good, but now the question is at what speed the rainfall occurs. So after this we have rain intensity. Rain intensity is basically the speed at which the rain falls. Speed at which the rain falls. We express this as millimeter per hour or centimeter per hour. So higher the intensity of rainfall, more is its erosivity. So generally the high intensity rains these are associated with shorter duration, whereas low intensity rain is associated with longer duration. And if the combination is high intensity rain, longer duration, this definitely will lead to flood hazards. So we have to be very careful. So generally these again high intensity rains, these are characteristic of tropical regions, whereas low intensity rain with longer duration, this is the characteristic of temperate regions. But now due to the change in climate which is happening all over the world, we are observing that high intensity rains are occurring with longer duration. That's why every alternate year we do have floods over here and there at the global level. So basically if I say, if I draw a curve of say this rain amount and time, so if it's a cumulative curve, so this is how this slope of, that means rain, this is your what we call as rain intensity. So, here it is amount of rain divided by time. So, rain intensity is basically rain amount over time, and generally we express this as centimeter per hour or millimeter per hour. So, again higher the intensity, more will be the erosivity of the rain. So, this is the third parameter. Then another important parameter is drop size, rain drop size, because bigger the drop, more will be its kinetic energy, half mv square. But of course, kinetic energy is a parameter of velocity as well as mass of the raindrops. But again, then there is a relation between rain intensity and drop size. So, drop size generally is quite variable. Okay. So, rain drop size. So, this is quite variable size of drops. So, you have a spectrum in a particular rainstorm, you have a spectrum of raindrops starting from say 0.1 millimeter going up to 5 or 6. So, upper limit is 5 to 6 millimeter, because if raindrop size, if it exceeds 6 millimeter, it becomes unstable. If you have a bigger raindrop coming from coming to the ground, then it will be unstable. Why? Because of the more surface area, the frictional forces of the atmosphere, it cannot resist the friction forces. So, it gets broken down and then gets converted into, so it breaks down into smaller particles, smaller sizes, smaller drops. Now, as I said, you have a spectrum of raindrops. Then how you can say that what is the actually drop size or average drop size? In that case, we have a parameter called D50. D50 is basically median drop size where 50%, this is 50% of rain volume occurs with drop size lesser than this, and 50% occurs with drop size smaller than D50. So, this is how we come out with a parameter called D50. So, if a particular rainstorm has more number of bigger drops, D50 will be higher. So, if the same any rainstorm having more number of smaller drops, D50 will be lower. And then this D50 has a direct relation with your rain intensity. How? This is intensity. So, here for example, as I said, as the rain intensity increases, D50 increases till a time with further increase in rain intensity, I should better write it other way round. This is your rain intensity. This is D50. So here it is rain intensity. This is D50. This is in millimeters. This is in millimeter per hour. So as rain intensity increases, D50 increases. But with further increase in rain intensity, here D50 it decreases. Why? As I said that when the drop size exceeds 6 millimeter, it cannot resist the frictional forces of the atmosphere and it breaks down into smaller drops, and smaller drops ultimately come to the ground. So, this is how this is a relation between D50 and rain intensity. Of course, a direct relation up to 5 or 6 millimeter. After that, it does not have any relation with that. So, this is how and you know, as I said, bigger drops, they have higher kinetic energy, because this kinetic energy is 1/2 mv square. So, m is mass, bigger the drop, more will be its mass, and v is intensity of the rain. And as I said, direct relation between rain intensity and D50. So, you for determining the kinetic energy of the falling rainfall, or you can say to find out the erosivity of the rainfall, you have to know the D50 as well as intensity of the rainfall. Then you can have an idea how erosive the rainfall is. After this, we have raindrop size distribution. So, this is a raindrop size distribution over here. Next parameter, and the best you know, the parameter for this is D50, as we have discussed. So, now based on this, we have you know, till this time we have discussed quantity of rainfall, distribution of rainfall. So, first parameter was rain quantity or rain amount, then rain distribution, rain intensity, raindrop size, and then raindrop distribution, spectrum of drops, as I said, and ultimately the next parameter is then terminal velocity. So, let me rub this first. Rubbing is a big issue for me, but anyhow I have to bear with it. Even you people have to bear with it. I was very comfortable with that, you know, the duster, cloth duster and blackboard. So, maybe I am too old for this, you know, electronic gadgets or new technology, because it breaks down my tempo speaking. While speaking, I have to stop over here. So next parameter is terminal velocity. Now, what happens that supposing a raindrop, it is falling, and when it is falling, it is this is your ground, say soil surface, now this drop, when it is falling in the atmosphere under the influence of gravity. So, downward force is gravitational force, but at the same time the atmospheric pressure, it pushes it up. So, upward force is the resistance of atmosphere. Then at one height, this downward force becomes equal to the upward force. Here the two forces become equal. So, this, if I say this is d and this is u, then when d becomes equal to u, then this drop does not accelerate anymore. Drop does not accelerate anymore, and if it does not accelerate anymore, so here you can say it achieves a constant velocity. Otherwise, when it was falling down, as it was coming near the ground, its velocity increased. But when these two upward force and downward forces, they became equal, then the velocity did not increase any further. So, at whatever velocity was there, it started falling with a constant velocity, and with this constant velocity we call as terminal velocity. So, terminal velocity is the velocity of the raindrop, speed of the raindrop when it does not accelerate anymore, or when the drop falls at a constant velocity. And generally they say that when the drop it falls with the constant velocity, if it is falling from a 2-meter height, it can achieve the constant velocity. This is what people have studied. So, if you have say drop of 1 millimeter, 1 millimeter drop, its terminal velocity will be 5 meters per second, and if same drop is of 5 millimeter, then terminal velocity will be 9 meters per second. This is what people have made. So, the terminal velocity basically it is a function of the size of the drop. And then the last parameter is momentum and kinetic energy. Momentum and kinetic energy. Kinetic energy, as I have already told you, basically kinetic energy, this is a combination of mass of raindrop and size. So, that is raindrop size and mass, because bigger the size, bigger will be mass, and then velocity means intensity. So, when you combine intensity with raindrop size or raindrop mass, you get kinetic energy, and momentum is your mass into velocity. That is, there is a particular speed, the two bodies of different masses, if they are running with the same speed, the momentum of the body with greater mass will be higher than the body with the. Similarly, when there are two drops 5 millimeter, 2 millimeter, their velocities will be of course different, but because the size, even if their velocities say you have two drops of the same size, their velocities could be similar, but at the same time if size differs and velocity, they are coming with the same velocity, before achieving the terminal velocity, the momentum of drop with bigger drop will be more than the smaller one. So, this is how we determine, but the most important parameter is kinetic energy, and I have already discussed the erosivity indices. The most important erosivity index is kinetic energy greater than 25 millimeter per hour. Even EI, erosion index, particularly erosivity index, that is the kinetic energy of the rainfall, different intensities of rainfall clubbed together, the total energy of rainfall, That is one index, and in some parts people said that there is, if the rain is falling with intensity lesser than 2.5 centimeter per hour, it's not erosive. So they calculated the kinetic energy of the rain with bigger intensity, higher intensity, 25 millimeter per hour. So this is what on these parameters the erosivity indices are based, and you can have an idea about the erosivity of the rainfall and how it causes erosion. So I think that's all. Thank you very much for today. So we will discuss these topics next time.